I wanted to take a break from talking about the Euclidean algorithm and invertible elements mod n to go over lab 2 on how to break a Hill cipher. I hope to post those grades today or tomorrow. By the time you listen to this, they might already be posted. I've just been super swamped with all this coronavirus stuff and trying to adapt everything for online stuff. But let's go ahead and talk about how to break a Hill cipher, because you will need this knowledge for your midterm exam. So as you experienced in the lab, it can be really, really hard to break a Hill cipher. It's a pretty decent cipher, to be honest, so that's not a surprise. Not all the groups were able to do it, and that's understandable. So in this handout, which I'm going to break into two parts, part 1 and part 2, we're going to talk about some of the features that make it hard to break, and some of the features that, surprisingly maybe, make it really easy to break. And as I mentioned before we left, this is going to be important for us to understand when we start talking about modern crypto routines like RSA and Algoma, to understand and appreciate why they're so good. So what I'm going to do is I'm going to run through the strategies for breaking the Hill cipher, and I'm going to break it down by the kind of attack that you could use. So just remember that we're encrypting by multiplying blocks by some mystery unknown key matrix, ABCD, which has to be invertible. So your job is to find the matrix A, which is the same thing as finding out who the entries A and B and C and D are. So let's talk about how you might approach this. First of all, good job. No one really tried to brute force this thing, and you shouldn't, because it's got maybe surprisingly over 150,000 keys, so not really a good idea. So let's talk about the first kind of message attack, which is known ciphertext. So this is really the baseline for what you were given in the lab. You were handed a piece of ciphertext, and that's it. And so if that's all you have, then you're just working with known ciphertext, period. So in order for this to work, you have to make two really good correct guesses on bigram frequencies, so 2-letter frequencies in the plain text and ciphertext. This can be quite hard, okay? You have to get really lucky for this to work. The best guess you can possibly make is that if the original plain text was really good English, it had a lot of these in it. So the most popular bigram should have been TH, and the second most popular HE. If that is not right, I'm not sure what to tell you. It's just hard to say. So here's an example on how you would do that. Suppose you make that guess, and the two most popular bigrams in your ciphertext, which is not a guess, you can look it up, are JY followed by QT. Assume that. Then you know that TH is 19.7, HE is 7.4, JY is 9.24, and QT is 16.19. So you guess that TH will go to JY. So you're guessing that 19.7 will encrypt to 924. Write it down. Key times 19.7 is 924. In the same way, you guess that HE goes to QT. You are guessing that 7.4 goes to 16.19. Write that down. 7.4 encrypts to 16.19. So here's the nice trick. Realize that at this point, matrix multiplication is really two parallel vector multiplications. So you have A times 19.7 going to 924 is the first columns down here. A times 19.7 goes to 924. A times 7.4 going to 16.19 is the second columns. A times 7.4 going to 16.19. So now I have these two separate equations as one. This is very powerful. This is now only one equation. If I can solve this equation for A, I've got the key. This is not bad to do, not too hard, because, let me leave this on the screen, this guy right here, which I'm calling B, the right-hand guy on this side, is hopefully invertible. In this case, it is, right? So if you call this guy B, if I can invert this, I can multiply it off by the inverse and get A. So here's how we do it. If you let B be that term, you can use our formula for the inverse to see that it's invertible, and here's the inverse, okay? So here's the equation I just pointed to you. A times B is the right-hand side, but I know that B is invertible, so you can multiply by the inverse to B on the right and actually get the key. So this will work. This will work if your TH over HE guesses were correct. If either one of these is wrong, this will not work. So the stars have to align just right in order for this kind of attack to work. So I want to point out that at least 2 groups figured this out during the practice round. So that's a good job. If your Lab 2 plain text did not have TH over HE, then this wasn't going to work. Let's move on to the next kind of attack, which is known plain text. So here you have a piece of plain text and you know what it encrypted to, and you know the same key was used. So that gives you some information. And so you ought to try sort of the same thing above, because now you're not making guesses anymore, right? You're no longer guessing the plain text bigrams because you know the plain text. Let's do the example. I think almost every group in the class bought the hummus. And so that gives you 3 plain text blocks that you now know what they do. That gives you the block HU, the block MM, and the block US. So suppose you bought the hummus and it encrypts to, for example, XFGQOO. So if you match the blocks, this tells you that HU had to encrypt to XF. That is not a guess. That's not a guess. So HU is 720, and that had to encrypt to XF. So now you know that A times 720 is 23.5. Write out what A is. A is some mystery matrix ABCD, and do the math. This says 7A plus 20B is 23. That gives you an equation. It also tells you that 7C plus 20D is 5. You now have 2 equations to play with. But you also had 2 other blocks. So if you did that for double M and US, you now have 6 equations to use. If you mess around enough with those 6 equations that you get from hummus, you might be able to get the key. And some groups did. That's good. Okay? But that's all you can do is look at what I'm doing. I'm simply writing down what I know. The block HU had to go to the block XF. Write it out in terms of your key and play with it. But you can do it 2 more times. You can do it for that one and do it for that one. Okay? Some groups did that with success. That's good. Now, just to point out here, the pot roast was a better bargain. It cost the same amount of money. It was still a point. But it's a little bit of a better buy. For one reason, you get more data. You have 4 blocks, right? You have 8 symbols, so you have 4 blocks. You have more data. That's a good reason to buy it. The other good reason is that A is a 0. And if you had a 0, a lot of these will die off, and that might tell you what A or C was, because you can cancel that 7. It's a unit. So pot roast was a better buy because it has an A in it and because it's longer. No one bought it, though. That's okay. We're learning. I don't care. So I'm going to stop right here, and I'm going to save the best attack for the last page because it takes a while to explain, okay? But look at this, see how to make use of the hummus, and understand why this is hard, okay? Understand that before we go into the next page. See you in a bit.